So camphor. So this is a natural product, right? So you guys have heard of natural products. A lot of times they're drugs that are derived from nature that we either make in chemistry labs, or we actually have bacteria make them, or we actually isolate them from nature, right? We grind up a tree bark and isolate these things. So this is a camphor tree. So this is actually where camphor comes from. So camphor has a pretty long history. They call it a terpene. Have you ever heard of terpenes? They're these things that plants make. They're always in 5 carbon units. So you maybe heard of monoterpenes or diterpenes or triterpenes. It was first synthesized in 1903. You can probably smell in here. You smell it kind of smells like Vicks Vapor Rub. You guys getting that at all? That's kind of where this is coming from. So it's been medicinal. They've used it in embalming fluid, moth repellent, fireworks, lots of different uses for it. And people kind of use these natural products, whether they realize that they're there or not, they've been using for a long time in history. So this is where chemistry kind of comes in. So this is the camphor tree. So this is where it actually is derived from. So that's where they actually isolate this tree. So lots of people have been using this for years because they realize there's medicinal properties. And the medicinal properties were coming from the camphor from the actual camphor trees, right? So they grind up the leaves and they, maybe make tea, or maybe they isolate the compound, and that's what's actually giving some of these medicinal properties. So, like I said before, it's a terpene. There's over 20,000 of these known. And it's really cool because what nature can do, nature can take this terpene here, right? This diene, something we've seen a lot. This diene, and it can make multitudes of different molecules from this. Right? There are always multiples of 5 carbons, but nature can do lots of really neat things with this isoprene, this repeating unit. They can make things like limonene, which is like the lemony smell that you can kind of get. They also make things that are chiral, right? They have handedness, right? So not only is nature good at making things, they also can make things in specific ways, right? Drugs have handedness, right and left-handedness. These carbones are really interesting because one of them smells like spearmint. The other one's much more like molasses. Like, it's the same molecule. The only difference is it R or S? But your nose receptors are, right? Your receptors in your brain, in your body, are also R and S. So they actually interact different ways, right? Based on that. And then, of course, the one we have today is camphor, which also has an R and S, right? A chiral center as well. This is just showing. I'm not thinking if anybody realize this or know this, but this just kind of, I think it's fun because it shows, right, this pyrophosphate, how nature kind of does this, how our bodies can do this. They can essentially do these are called cascade reactions, where essentially there's a lot of arrows at once, but you can take these terpene things, right, and you can make all sorts of different things from it, right? It's kind of wild how they can actually turn these things into different things. So I think that's really cool to just kind of see what our bodies are capable of, to see these different reactions. I can't do this in a flask, right? It's really hard, but our bodies can do it no problem. Terpenes are also, right, they're found in steroids, carotenoids. So again, anytime you see these, if you see something that's C20, C25, C30, that's probably a terpene, right? Because those multiples of 5. But again, these are really different molecules, but our bodies can make these, or plants can make these. Organisms can make these based on this chemistry. Another cool application, I think actually Professor Beckman used some of these catalysts when he was in graduate school, was because these things have chiral centers, they have R and S characteristics. Chemists and biologists and biochemists can take these and use that chirality to their advantage, right? And use it to help make new chiral centers, right? I always think of, if you're right-handed, if you put your right hand into a beaker, imagine you suck your right hand in the beaker. Because you stuck your right hand in, that's going to affect that reaction and maybe make those molecules right-handed too. Versus if you stuck your left hand in there, right, don't stick your hand in a beaker, right? But if you did, right, that's what a chiral catalyst can kind of act like, right? And so taking chirality from nature and then using it for chemistry is really a cool, powerful way to do things. And camphor has been done to do that. So compounds that easily sublime. The reason we're smelling that, right, what does sublime mean? It goes from solid to gas. Right, so compounds that easily sublime, right, have high solid vapor pressure. They're very nonpolar. A lot of times they're spherical or symmetrical, right? So naphthalene, this is like mothballs. So camphor is actually like that. You can actually, right, we can smell the camphor. It's subliming, right? So a lot of different compounds do that. This is a fun picture of the 3D structure. I always think we forget, right? Molecules exist in 3 dimensions, right? We always draw them on 2 dimensions on the board or 2 dimensions on my iPad, but right, there's a lot of space, right? There's hydrogens there. There's a lot of things going on, right? And that's important to think about when we think about stereoselectivity, right? So our nucleophile is H minus today, right? H minus. And it can either come from the top, and we call that an exo attack, or it can come from the bottom. We call that an endo attack. You get 2 different products, right? We get these 2 different diastereomers, which then have different physical properties, right? Diastereomers have different melting points, different boiling points, different IRs, different NMRs, right? And that's what we're showing here, different NMRs, right? So if the H comes from the top, this H is on the top, which sees these hydrogens differently than this H on the bottom, right? Doesn't see those hydrogens. So we're going to get a different shift, a different chemical shift because of that. We're making diastereomers. Now, one of the questions we could ask and think about is, well, why would something want to come this way versus this way? Well, what do you guys know about addition reactions or substitution reactions? We know about sterics, right? Coming from the top might be pretty hard, right? You see all this stuff here? It's kind of in the way. But then what kind of product does it make? Does it make the more stable product or the less stable product? I don't know, right? Well, let's think about this. Is this more stable or less stable? This OH is on the bottom. What do you think? Remember learning about axial and equatorial? Axial, this kind of looks like it's kind of axial, right? If you remember, axial stuff was always kind of crowded, right? It's kind of in the way. And equatorial is kind of sticking out. So this looks like it might be the harder path, might take more energy, maybe more, right? Thinking about kinetics, but maybe it makes the less stable product, right? So it's actually both there. Whereas if you have the endo attack, right? You get the H on the bottom and the OH sticking out, the bigger group sticking out, that's probably a more stable product, right? So at least looking at the products, I know this is probably more stable because this is kind of this exo or equatorial, whereas this OH is in the endo phase or kind of axial. But I don't know. One thing I don't know is the activation energies, because I don't know. I'm guessing right now that this will take more energy, but I'm not sure. We're going to find out. Right? But I can look at the products and kind of have an idea of which one's more stable, right? So, well, let's think about this again. Which one's less favored? Actually, right, like I said, the exo attack coming through all this junk up here, the H coming from the top, getting the O on the bottom, is actually less favored. And then we think it makes the less favored product, right? The less stable product too. So the endo attack, come from the bottom, might be more favored, take less activation energy, but it also gives us the more stable product, right? So this product in theory is both the thermodynamic product, it's the most stable product, and it's the kinetic product because it comes from the lowest transition energy. So it's both the kinetic and the thermodynamic product in this case, we think. I'm not worried about the mechanism here. All I want you to realize is sodium borohydride has how many hydrides? 4. 4, right? For every sodium borohydride mole you put in there, you get 4 hydrides out, right? So technically it's worth, you can do a 4-to-1 ratio. That's all this is trying to say. Here's the NMRs. You have these as well. So this is what if we're looking for isoborneol, right? It'd be at 4, right? See that peak there at 4? That's borneol. Isoborneol, we said would be around 3.6, right? So we kind of have an idea what we're looking for in the NMR, right? That oxygen is very electronegative. It's going to pull electron density. It's going to make this H de-shielded. If you're de-shielded, you go where? You go downfield, right? De-shielded downfield. If it's borneol, it's at 4. If it's isoborneol, it's at 3.6. We're predicting isoborneol more than we are borneol, just based on the mechanism. Think about the mechanism. And then, of course, here is the starting material, and notice the starting material has no OH, no H's around 4 or 3.6, right? Because once you put a hydrogen next to that oxygen,